Yeah, thank you for having me. Really happy to be here. So, my name is Jonathan Adams, and I was part of Dr. Arthur Compton's team studying the scattering of X-rays by electrons in the early 1920s. So, our project, which is the now famous Compton's X-ray scattering experiment, demonstrated that X-rays, previously thought to be only waves, can also behave like particles. So in 1922, at the Washington University in St. Louis, we observed that when X-rays collide with electrons, they recoil like particles, conserving energy and momentum in the collisions. And this phenomenon is known as the Compton effect now. And this was groundbreaking because it provided the first proof that electromagnetic radiation, like X-rays, has a particle-like nature, confirming a prediction that Albert Einstein had made years earlier that we call light quanta. And our findings, they went on to spur major developments in modern physics, especially in the rise of what is now called quantum mechanics. So we set out to investigate how X-rays behave when they scatter off electrons, and specifically to test whether X-rays would transfer energy and momentum as individual particles. And at the time, there were many scientists who still doubted that light could act like discrete particles. Dr. Compton wanted to see if an X-ray photon bouncing off an electron would lose energy in a way that a particle collision would predict. In other words, we were looking to see if the wavelength of the X-ray increases after scattering. And this would tell us that the X-ray gave up some energy to the electron. And indeed, our hypothesis was that the scattered X-rays would have slightly longer wavelengths than the incoming X-rays. And this is a signature of the billiard ball type collision between a photon and an electron. This idea is based on the then controversial theory that light quanta carries momentum. And this was an idea that was proposed by Einstein back in 1905. So by conducting this experiment, we hope to find clear evidence that either for or against that particle theory of light. So in late 1922, Dr. Compton sketched out the theory. A photon, an X-ray quantum, strikes a stationary electron. They recoil, and the energy momentum is conserved in the process. Our goal was to verify this experimentally. And if it were successful, it would show that X-rays act like tiny particles in collisions, that is. And in fact, that's exactly what we found. The X-rays that scattered off the electrons had measurably reduced energy, longer wavelengths, just as the particle theory predicted. Yeah, so our experiment was conducted at Washington University in St. Louis, Missouri, and it was conducted in the physics lab, which was in Eads Hall on campus. So at the time, Compton was a professor and the head of the physics department at Washington University, and the university had the lab equipment necessary to do the X-ray experiment. So we set up the apparatus in the basement of Eads Hall, actually, and this is where Compton had been doing his X-rays research. So the entire project was done at the St. Louis, and it's worth noting that after finishing this experiment in 1923, Dr. Compton moved to the University of Chicago, but the pivotal Compton effect experiments, they were all done at Washington University in St. Louis. yeah, so our experiment took place in 1922, and a lot of things were going on in the world at that time. For example, Howard Carter, and he's an English archaeologist, made headlines for discovering the tomb of the pharaoh of Tutankhamun. I can't say his name, and I thought that was really cool. This was in Egypt, of course, and he unearthed treasures that were hidden for over 3,000 years. And also in the end of 1922, that's when the Soviet Union came about, of course. Also in the scientific community, 1922 was a really noteworthy time. Niels Bohr he received the Nobel Prize in physics for his atomic theory. So it's a really dynamic time globally. A lot of things were happening, and a lot of scientific achievements also. So Dr. Compton was, of course, the leader of this experiment, but there were a few other people who were really key to the success of this. And one of those people was Dr. Alfred Simmons, who worked closely with Compton to design and build these experimental setups. And Simmons' contributions were really vital to the success of these experiments, and they were important in allowing us to detect the X-rays and electrons coincidentally, which was a real technical challenge. We also had a few laboratory assistants and graduate students like myself who handled various tasks such as setting up the X-ray tube or operating it, preparing the targets, and taking measurements. And while they weren't directly part of our project, I think it's really interesting that over in Germany, so I was essentially a junior assistant in Dr. Compton's lab. I took part in a lot of the hands-on experimental work. So my role involved setting up and running the apparatus as well as recording data. For instance, I helped prepare the X-ray source and the target material. In our experiment, we used a high-voltage X-ray tube to produce X-rays that we would direct at a block of graphite, which served as a scattering target. So I was responsible for calibrating and operating the rotating crystal spectrometer that we used to measure the wavelength of the scattered electron rays. The X-rays, not the electron rays. So this spectrometer had a crystal that we could rotate to diffract X-rays at various angles, allowing us to precisely determine any shift in the wavelength of the scattered beam. I also manned the movable ionization chamber detector, which we used to measure the intensity of the X-rays coming out at different angles. So essentially, I spent a lot of time adjusting the angles, monitoring the instruments, and reading the photographic plates so that we could see how the X-ray spectrum changed after scattering. I also helped with some of the calculations and analysis. For example, comparing the measured wavelength shifts to the predicted value, to Compton's predicted values from his formula. So, in summary, my role was to keep the experimental setup running smoothly and to gather accurate data for Dr. Compton. Our project has had a tremendous impact on physics. It's really truly changed the way scientists view light and matter. First and foremost, Compton's experiment proved definitively that electromagnetic radiation also has a particle aspect to it. And this finding confirmed Albert Einstein's theory back in 1905 that light quanta carries momentum. So by showing that the X-ray could impart energy and momentum to electrons, we forced the scientific community to accept that light is not only a wave, but consists of particles in certain interactions. The experiment's outcome has really opened the door to the quantum era. And in fact, Werner Heisenberg, who is a physicist, later cited Compton's discovery as the key event that opened up quantum mechanics, the path to quantum mechanics. Many breakthroughs in the quantum theory that followed were built on the notion of wave-particle duality from Compton's experiment. The significance of Compton's work was quickly recognized. He was awarded the Nobel Prize in Physics back in 1927. And since then, his work has been the staple in physics textbooks. It's one of the classic experiments demonstrating quantum principles. Our project also influenced other experiments. For example, after initially doubting our results, many physicists, such as William Dewey, performed their own tests, and they ended up confirming Compton's interpretation. So, in summary, Compton's experiment, it's been profound in the physics community. It's validated the particle nature of light. It's helped establish the foundation for quantum mechanics, and it's earned a widespread acclamation due to its pivotal role in the understanding of atomic and radiation physics. Yeah, absolutely. So the Compton's effect, it's not just a cool little science fact that we discovered. It's actually become a super important practical application in modern science and technology. For instance, it's used in medical imaging, where we use the principle of Compton's effect, or of Compton's scattering, in techniques like the Compton scattering tomography, which is used to help form images of the interior of the body or any object. So by analyzing how X-rays scatter, we can map out density variations in tissues, and this helps us improve image contrast in certain types of scans. It's also used in radiation therapy for cancer treatment, and understanding Compton's scattering is crucial for this. So as a high energy X-ray or gamma ray beam passes through the body, they undergo Compton scattering. And our knowledge of radiation really helps the medical physicists calculate how radiation doses deposit in tumors versus in the healthy tissue. So these treatments can be planned safely and effectively because of this. Beyond medicine, Compton scattering plays a role in astrophysics. There's a phenomenon called the Sunyaev-Zeldovich effect, where cosmic microwave background photons scatter off of high energy electrons in galaxy clusters, and essentially a giant scale Compton scattering event. So astrophysicists measure to learn about galaxy clusters and large-scale structure and the large-scale structure of the universe because of this. In addition, there's something called Compton telescopes, which have been developed to detect gamma rays in space by using multiple scatterings. This is called gamma ray astronomy. So closer to home, techniques in materials analysis and security also rely on Compton scattering. For example, industrial scanners can use scattered gamma rays to gauge the composition of materials in a non-destructive way. So to summarize again, the Compton effect has really helped uncover and become a foundational principle applied in imaging, radiation technology, and astrophysiological observations. A great example of what was once a purely academic discovery, finding its way into real-world uses.